And at this point, we will look at the different k values here. To get our solutions of this equation, we can take k equal to 0. And we know the magnitude of the number is 1 for all of these. And for k equals 0, we have that our angle would just be 0. We have 0 degrees plus 72 times 0. So theta is 0. And for k equals 1, we have that theta would just be 0 plus 72 times 1, or 72. And we could, of course, write this as 2 pi over 5. We have when k is equal to 2. Now we do 72 twice, and again, plus 0. And that would be 144 degrees. And if we want this in radians, it would be 4 pi over 5 radians. Now we need the other cases. We'll do k is equal to 3, meaning we're adding 72 3 times. So theta would be 216 degrees, or 6 pi over 5 radians. We can do k equals 4. Here, theta would be 288 degrees, or 8 pi over 5 radians. You can see it's a little bit easier to do this in radians for this particular case. And these are the 5 solutions that I mentioned, but just to show you why we only need 5, we will look at k equals 5. Since k is an integer, it could be any number, any whole number that we want, positive or negative. But when it's equal to 5, we are multiplying 72 5 different times, and we get theta is 360. But we know 360 can be rewritten as 0 degrees, and we already had a solution for that. So we don't need to rewrite it again. We're just finding the same value, meaning that this case is redundant. We just don't need it. And for k equals 6, it will reproduce this one. This would be 7, 8, 9, and then 10 would again go through the order. So we just need those 5 solutions. And in fact, whatever we are raising this to, that's how many of these integer values we need to consider. And since we're raising it to the 5th, we just needed 5 of these values. Now, to rewrite these numbers in their polar form, we can say that our solutions, our z is 1 multiplied by the cosine of 0 plus I times by the sine of 0. And in rectangular form, this is just equal to 1. And we can call this z1. That's our first solution. We can write for our second solution, it has a magnitude of 1, but now our angle is 72 degrees. And in rectangular form, this might get a little bit messy. We get an approximate answer. We would have to round this in rectangular form, but this would be 0.31 plus the imaginary part, which is I, multiplied by 0.95 or so. And we can write the third solution. That's with 144 degrees. We still have a magnitude of 1. Cosine of 144 plus I times by the sine of 144. And again, if we want its rectangular part, we would just have to write this as an approximation. So I will leave that as an exercise if you want to do that. Z4, we are using the 216 degree angle. This will be our fourth solution to that equation. Again, you can write its rectangular form if you choose so. And the last solution uses the angle of 288 degrees. Or if we want, we can put all of these into radians. And in fact, when we use radians, it's a little bit clearer what's happening on the unit circle. So let me draw a quick sketch of the complex plane. And if we start plotting these points, Z1 would be right here, a real part of 1. Z2 has an angle of 72 degrees. And if we plot these points, or it's 2 pi over 5 radians, that would be roughly somewhere around there. This will not be drawn perfectly to scale. Z3, that's at 144 degrees or at an angle of 4 pi over 5, so that will be maybe right about there. The fourth solution would be at 6 pi over 5 radians, or 216 degrees, so that will be roughly about there. And our last solution is at this 288 degrees. I will do that in this orange color. That will be roughly right about here. And when you write these numbers on the complex plane, you will see that there is a symmetry about them. Now, like I mentioned, I did not draw these perfectly to scale, but if they were drawn perfectly to scale, you will see that they all actually end up on a circle, where this circle is centered at the origin of this complex plane. And this will happen anytime we find the complex roots of some number. So if we had z to the 12th power is equal to 1, all 12 of these would be arranged on the circle. But this doesn't have to be equal to 1. This could be equal to any number we want. It's just the radius of this circle would then be the 12th root of 15. We would find the real value solution to that, plot that point, and that would be the radius of the circle. So in the next video, we will look at this approach using Euler's formula, which you will see is much more efficient at quickly finding these roots.